Software Engineering Radio Episode 87, Software Components.
This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast. Welcome listeners to Software Engineering Radio. Here are a bunch of announcements I want to make before we go on with the actual content of this episode. We need your help. Please help make SE Radio more widely known. Please consider submitting SE Radio to sites like Dig, Delicious, Slashdot, or something. We have those shortcut links on each episode page. This will help us make SE Radio, more widely known so more people can listen to the episodes. More fun for us because we have more listeners, more fun for those people because they now know SE Radio. So please help us make SE Radio more well known. Okay, and here is the actual episode. So, hello Michael.
Hi Markus.
Well, I think this episode is going to be interesting. We're going to discuss software components and component architecture, and I think we both have, at least about some aspects, we have both very specific opinions. So I guess this might be controversial at times.
Let's start with the definition of what components are, what we understand by the term component. Markus, do you like to start?
Yeah, why not? I mean, generally, component is a very much overloaded term, and the most generic definition is basically a piece of software that is somehow separately usable or separately deployable. If you build a system, then you have, for example, a server component and a client component. This is very, very generic and, in my personal view, not very useful. But people do use it that way. However, that's not the way we want to discuss it, as you'll see later. Another definition is, or another use, I don't know if there is an explicit definition, is you can find it in the graphical user interfaces world. And if you listen to the Java posse, you will probably know this discussion from the Naxal guy. What is his first name? I forget. And he says basically if you have classes in an object-oriented programming language which also have properties as well as events to which you can register, then that is what they call components. And that's in the tradition of Visual Basic or Delphi. They all had those component libraries for visual components typically to interactively compose user interfaces.
So I guess then one of the key intentions is the reuse of software. So that is how it all started, I believe, in the 60s or 70s when the first discussions arose.
It's this idea of being able, as I said, to separately use something and then, of course, to reuse something. So it should be a somehow well-defined subset of functionality that is, as the generative programming people like to say, that's minimally redundant and maximally composable, okay? So it should be composable with other components. The Lego brick metaphor, you can assemble your system from stitching components together.
And that's the reason why there is such an emphasis on interfaces, on defined interfaces that this component provides, as well as those that it requires, right? So basically the context of a component, in which environment can this software component then run? What does it need?
Absolutely. So that's one of the, in my view, really important concepts of a component. It should declaratively specify as much of its expected environment and of its provided services as possible.
Why declaratively?
How else would you do it? I mean, you need some metadata that describes it, or you need very clear, very specific, very, very clearly defined, let's say, idioms, coding idioms, so you can use some kind of reflection API or other tooling to inspect what a component does or depends on. Otherwise, you cannot build tools that build or compose applications by stitching together components because the tool cannot find out what a component does. it needs to be declarative or based on metadata. It's the same thing.
So the metadata is the key point, and this is maybe, I don't want to stretch it too much because then we get into the model-driven discussion already. But another important point is the deployability. You should be able to deploy the component in different environments, so it shouldn't...
it shouldn't have any implicit assumptions of the environment. All the environment dependencies must be explicit, so when you do deploy it in some environment, you can tell whether it's going to work or not, ideally statically. That's at least how I see it. So if we go back to other uses or definitions of component, the UML also has a notion of component. It's basically, if you remember the UML, it's basically this rectangle with these two small rectangles, I think on the left or right side. And they consider this more or less a deployment artifact. So they have this deployment view of what a component is. It's, in my personal opinion, not very useful.
Another thing that comes to my mind is the discussion about binary compatibility of the interfaces.
Right.
How important is that? I remember that the IBM SOM discussion really focused on this, as well as Microsoft COM technology did. Is this still relevant, this discussion today?
I personally don't see this as a defining property of a component. It depends on how you compose your system, whether you want to be able to compose the system by composing binary components, right? Then, of course, you have to be able to have this binary pluggability, and then you need the metadata somehow embedded in the binary distributable. But there is also a good use for components that are more relevant during the construction of software when you work with source code. In that case, there is no need for binary pluggability, I would say. So in my practical experience, typically, if you consider components as an architectural building block for building systems, then the binary pluggability is not an issue whatsoever. Okay,
and what did you want to say right now when I disrupted you?
Oh, I wanted to say that there is also this kind of classic definition by Clement Szyperski, which I think you looked up.
Yeah, this is one of the definitions I looked up, and there's one key property that he states is that it shouldn't have persistent state a component. And so, what is your opinion on that?
Well, again, we will discuss that later in much more detail. But I think what a component really is needs to be defined for a specific system. So there are systems where the architects decide that components are stateless. And in that case, components obviously shouldn't have state and also no persistent state. But there is also other systems where the architect says, well, there are either stateless or stateful components, and there are components that might have persistent state or non-persistent state, or there are components which themselves don't have state, but they manage access to a database, which is also some kind of state. So I think that the core is that it should be defined per project or per system in some kind of, as you say, we shouldn't get to the model-driven stuff too early. Some kind of meta model, right? Some kind of definition of what we consider a component is or should be in a project. And that can, in some projects, include state and not include state in other projects. That's my understanding there.
So what we realize is that it's really hard to give a broad and general definition of the term software component. But the core is, I believe, that you can use it separately, reuse it separately, and deploy it separately with only explicit dependencies.
Absolutely. And that's why this episode doesn't try to define it. We want to discuss how they're used, what their properties can be, what the typical variability is, and then of course it's important that in a specific project you actually define for your project what you mean by a component.
So why are components useful? You mentioned it already partly. Why are components useful, Markus?
So of course, again, this is my somewhat personal view. There is this traditional view where you say components, there is this component marketplace where people create components and then they are put in this global repository where people can then grab them and assemble their systems from it. I don't think this idea of component-based reuse has ever really materialized. I don't see that happening. And also it's kind of not fashionable today anymore, because today we all do SOA and we reuse hosted services. So I think components are useful for another reason. If we build systems with today's programming languages, then those programming languages are not able to express architecture. Okay? A programming language expresses, implementation code on a very fine-grained granularity. You have classes, you have procedures or methods or functions or whatever, and you have the implementations of those. But you cannot easily say how your system is created or composed on an architectural level. So if you compare components with object-oriented programming, then I would say that what classes are for the implementation, for the program, is what components are for the architecture. So they are an architecture's smallest relevant independent building block. So if you build a system, then you decompose your system into components. Those components have certain properties and responsibilities, and it's up to the architect to define what those are, and we'll talk about that. And inside the components, you might have whatever other paradigm to actually implement them. So components are the smallest architecturally relevant building block, foundation for architecture.
And what kind of, do you have other abstraction levels besides components then, or is basically everything a component and you would have hierarchical components, or how do you orchestrate this?
This is a very good question. First of all, it's important to say, and again, we'll talk about that later, there is also another side to component, which is in most systems that I build or see or work with, a component is not able to exist on its own. It's somehow managed, ran, or hosted by some kind of container or environment that provides additional services. We all know that from EJB or J2EE, where you put an enterprise Java bean into a container and it provides transactions and scalability and all that stuff. You know all that, so it's kind of boring. So in that sense, you don't just have components. You also have a container that hosts them. And it's up to the platform architect to distinguish what functionality goes into the components and which of the functionality is handled by the environment, by the container. However, I think your question was getting somewhere else. And I think what you kind of probably really asked was, assuming you already factored out this container, is everything else components? And there I would argue yes, because as I said before, in a project there can be, you have to define what a component is. There can be different kinds of components in a project. So you could argue that everything is components. Up to, or I should say down to, a certain level of granularity. Once you get inside components, then you implement them using whatever other technology, and then of course stuff isn't a component anymore. You already mentioned hierarchical components. I think we maybe discuss that later when we talk about what components, which variabilities they can have. But that basically means that you compose a component with basically interconnected instances of other components, and then you have a recursive structure. And if you argue that way, then of course everything is a component. Would you agree, or do you see it differently?
No, I mean, what I learn is that the way you use the term component is you define it in a specific context, and in the last sentences you define it in the architecture context, how components can help you to structure and align and basically provide a foundation of your architecture, so that you are enabled to structure your functionality according to technical concepts. It allows you an easier mapping later to technology. This is what I feel.
Exactly. That's also one of the core premises of the idea that a component description, if you say, it provides those services, it uses these other services and maybe some other metadata, which we talk about later, it's technology independent on the specification level. And then you can implement that component using OO or functional programming or whatever. And then you can use automated tools if you want, of course you don't have to then map that component to a certain, environment or container or technology. And that gives you a degree of freedom between the component its metadata and the implementation on one side, and the technology choice that's governed by non-functional requirements, and hype, I guess.
Okay. Before we go into further detail, I'd like to have one discussion that I really needed to grasp and understand the concept of components. This is, are components, do components require object orientation, or what kind of implementation technology, concepts, classes, whatever do I need to really provide and implement components? Do I have to use classes? Is a class already a component? This was pretty confusing for me as a beginner some years ago.
In my view, components and object orientation and classes are more or less unrelated. So let's elaborate a little bit on this. For example, you can have a component which is internal. Well, okay. So assume you define a component using all kinds of metadata, and then the question is, how do you implement it? One way to implement it is you can take a class in an object-oriented language and say, this class represents, let's say, the facade, the external view of the component. It implements the interfaces the component provides, and it has, using some kinds of patterns and idioms and framework stuff, it has a way of describing and accessing the resources and all the other environment things that it needs to access. In that case, you do use a class as an implementation artifact of a component. However, inside that class, of course, you might have 15 other classes and 287 objects and 57 methods. So that's a granularity thing again. However, you can also say that a component, another kind of component, is implemented by business rules, right? So you take a rule engine or some kind of rule specification language, whatever it's the language of the day. I mean, there are various open source tools. You can also use Prolog or whatever. And then the implementation is not object-oriented at all. And you can implement it with this other technology. So one of those, I think, key realizations is that if you build a system from components, then there can be different components. Some components are, let's say, standard business logic components. They're implemented using OO. Others are rule components. They're implemented by a set of business rules. Others are process components. They're implemented by people or BPMN or some other process description formalism. Others describe state-based behavior, in which case they publish events they can work with, and then internally there's a state machine that is triggered and then runs around. So in that sense, OO is one way of implementing components, or in other words, of providing the implementation code for the functionality the component wants to provide. Okay, so there is no direct relationship.
That is what I was aiming at, right?
Mm-hmm.
So maybe another confusion is that how do you relate a component to a class versus to an object? Like an object is an instantiated class. The class is only the plan for this object, for this kind of object. Now, what is a component in this context? Is it more a plan or is it more an instance?
Yeah, this is one of my favorite topics because it creates confusion in almost every project I'm involved in. So here's my personal opinion. A component is like the class in the sense that it's instantiatable. So there is components and there is component instances. There is no other word for it in my view. And the component instances are instances of the component, like objects are instances of classes. So they provide values for properties. They, whatever instantiation means in practice. This also somewhat depends on the definition of a component. However, there are systems where there is always only one instance of a component, in which case it is kind of pointless to distinguish components and component instances. Let's look at an example. Let's look at an embedded system, and you want to describe a vehicle with components, a personal car, and you want a component that controls the window, right? The electric windows. You can press a button and the component runs an engine, some electrical engine, that motor that drives out the window or down. Then you have a component which you would call window controller, okay? And it, for example, knows how to talk to the electrical motor that controls the window, and maybe it has an input that is fed from some kind of switch that is triggered by the window if it reaches the top position. So now a car has 4 windows. So it's kind of obvious what you do. You define your window thingy component, and then you have 4 instances of that, one for front left, front right, back left, and back right, okay? So in that case, it's kind of obvious. Also, if you have hierarchical components, then it's probably not obvious because that's where the discussions are all the time. But I think if you think about it, it's obvious that if you compose a component from other component-like things inside, then these are component instances. Because if you look at the car as a whole in our example, you could describe the car's software itself as a component, which is then kind of instantiated for each car you actually build. And then, of course, each of the things inside a component are, of course, themselves instances. It's also like an object orientation. If you define a class, then the class doesn't contain other classes. It contains objects, right? Variables, which are basically objects, and the behavior or the functionality, the implementation of a class is composed by stitching together objects, not classes. I mean, yes, there are inner classes in languages like Java, but let's forget that for a moment. The classical object-oriented programming defines new types by connecting instantiated other types and writing algorithms around it. And it's the same thing in components. A component is something that can be instantiated and then connected with other components.
So now that we had some of the basics, why don't we get into more details? And so what is really necessary? What should a component specify? What should the metadata contain and specify for the component?
Yeah. Let me step back like a half step, and that is, assume we have defined what a component is. How do we describe a system that is made from components? And I think it's obvious from the discussion we had before about the instantiation stuff that a component-based system is basically a system that is made up of connected instances of components. So if you define a system, what you do is you take your bunch of components you have in your library, you instantiate them, and then you connect them, and the connection thing is what I want to get at. A connection is basically if some component says, I provide this service, and the other component says, I require that service, then you should establish a connection, a wire or a connector between instances of those components so that the one instance of that one component knows which of those other instances actually does provide the specific service it requires at runtime. So that's important. So if you describe a system, you have typically several viewpoints. One viewpoint describes the components. We just discussed that with whatever properties they have. See in 5 minutes. Another viewpoint describes the composition, which is instances of those components and how they are interconnected. And then a third viewpoint typically describes the deployment or the system view, where you say, I want this component to run on some kind of server machine, another component on some other client machine. Well, I should have said component instance, sorry. And then you also map them to certain execution infrastructures like whatever, J2EE or EJB, whatever. So these are the kind of three main viewpoints, and that kind of leads into the discussion of what metadata it needs. If you want to describe a system, the metadata needs to describe the components, it needs to describe the instances and their connections, and it needs to describe the allocation of the instances to execution containers and hardware. That was kind of the system view. I think your question was targeted towards what a component as a type specification should include in its specification.
Yeah, so maybe we could differentiate between the absolute minimum, the core, and some typical or nice to have or common properties that components in today's technologies typically specify and require.
Yep. So the minimum is the interfaces or services it provides and those it requires. So that allows you simple dependency checking, so you know a system is only able to work with if all required services of all the instances you have are basically satisfied by provided services from other instances. One way of deciding whether this is minimal or not is simply to look at existing technologies. And if you look at typical today's dependency injection frameworks like Spring as the most prominent one in the Java world, and I guess Spring.NET in .NET, then that's exactly what they do. You describe the services you provide by having a class that simply implements certain interface, and you describe the services you require by using certain dependency injection conventions, either with setter methods or constructor parameters. So to recap, I think the minimum is describe which interfaces you require and which interfaces you provide. Since we talk about interfaces, well, if you listen to us discussing here, this probably sounds to you a little bit like the typical RPC kind of thing, right? Like Carba object or something. So an interface is a collection of methods you can call synchronously, blocking, and so on. And it's important to address that that's not the case. An interface is simply as a way of specifying how to interact with a component. And such an interaction can either be synchronous synchronous procedure call based, in which case you have the typical interfaces as you know them from Java or Carba or whatever OO language. But you can also have a message-driven system, in which case a component defines a bunch of messages it can understand and other messages it kind of sends out, it publishes as its interface. So in that case, an interface is a bunch of messages and maybe a specification of how these messages relate. This is typically known as interaction paradigms, message interaction paradigms. So you say things like, this is a request response paradigm where you accept the request message and then reply by one response message. Or there's another paradigm, the publish subscribe, where somebody sends you a subscription message and then you send periodic updates of whatever thing you want to tell these other clients periodically. So this is different message interaction paradigm. So an interface has to specify those.
And this is exactly something that the architect would typically define at the beginning of a project, what kind of interaction the components should have. And I guess it also depends on the technology, but very much on the famous non-functional requirements of the project, whether it's highly asynchronous or whether synchronous invocations are sufficient.
Absolutely. And it's not so much necessarily technology dependent, because you can simulate like RPC style stuff through message-oriented middleware, and also you can have asynchronous and more decoupled things using things like Carba. So it's more really, as you said, it's an architect understands the requirements, understands non-functional requirements, and then people discuss and decide, okay, our system should be primarily message-oriented, in which case you will define components whose interfaces are, as I said, those message interaction schemes.
So is this a minimum, or is this already some extended set of property?
The definition of interfaces is minimum. How else do you specify something that it does or depends on? If you look at the message-oriented world, then I would say formally defining interaction paradigms with protocol state machines or something, that's beyond the minimum.
Okay, what else? Anything else for the minimum specification?
I don't think so. I mean, for the minimum,
it's the interfaces, the provided and required ones,
right? And
everything else is then depending on the context on the project.
The interfaces are independent of components, right? So you don't say a component owns some kind of interface, because that would mean nobody else could use this interface, and that's kind of pointless. So interfaces are contract specifications that are their own, they live on their own, and components can then say, I provide this interface, and others say, I require this interface. Let's look a little bit at how you can give more semantic meaning somehow to components. You said before, or you asked the question, is everything a component? And I said, kind of yes. And assume a typical enterprise system. You have stuff that happens on the client that has a visual representation. Other stuff happens on the server and typically provides database access. Other stuff also happens on the server and does some business logic computations or calculations or algorithmic stuff. So the question is, can you distinguish those, and how do you manage dependencies? Because typically what you say is, yes, it's possible that a GUI component can access a remote business logic component. It's also allowed that a business logic component accesses a database management data something component, but not the other way around. This is the typical layering stuff, which we know. We all know that layering is a very good thing for big systems. And one way you can easily merge that with the idea of components is that you associate each component or each component type with a layer. You say you do have three kinds of components: GUI components, business logic components, and database access components. And then you define what the allowed dependencies are, like GUI can depend on business logic can depend on database, but nothing else. And then you can easily check when you specify or build a concrete system, you can use some kind of constraint checker that says, hey, you have just violated your own rules, which is that the dependencies can only go in this direction.
And another property that comes to mind is versioning. I mean, we discussed in the beginning that the reuse is so important, and now you start off with your project, use the component the first time. Now every system evolves typically. And what's in version 2? How can you properly differentiate between the new generation, the new version of a component? How can you make sure that your system really uses consistently the new component version? Little technologies have, in my mind, in my understanding, versioning support built in.
Yes.
I know .NET has some versioning support, and some IBM, some in the past did have, but Corba didn't really provide good versioning support, usable versioning support.
And the problem with versioning is, of course, compatibility, right? If you want to make sure that if you have a new version of a component, that the environment of that component can still use the new version without kind of crashing. So you can want a pluggable plug and play, right? You want to replace an existing version of a component with a new version, and the system should still work.
You want to have seamless upgrades if possible. I mean, that is something that users are just so used to. I don't download every new component of this new piece of software, provide a consistent subset that then installed, deployed, will work together and not fail because of missing interfaces or stuff like that.
So let's think about, first of all, what it means to be compatible. It means that a new version of a component provides all the services of the old component and maybe more, and that it does not depend on additional environment, right? So because the system might not provide that environment, so you cannot plug it in. So that's one of the constraints. And if you look at it a little bit more semantically and think about pre and post conditions, which is, by the way, also something you can associate with interfaces in components if you want, then this means that the precondition of some operation or interaction must be the same one as in the old version or others, because it can handle the old stuff and more stuff. And the post condition is either the post condition from the old one or a more specific post condition. So you OR the preconditions together and you AND the post conditions together. So that's more the semantic view. But the key to making versioning possible is primarily metadata, right? So what you want to do is you want to say that this component here is a new version of that other component. And then if you have sufficient metadata, you can again run a constraint checker that verifies that this new component actually does provide all the services of the old one plus optional new services, and that it does not have additional environment dependencies. So it's all about metadata. Once you have the metadata, you can run the checks, and then you can statically verify that if you replace this component with its new version, it will work.
But there are no syntactical conflicts. The semantical are always a bit harder, and here you need conventions or rules or stuff to fill that into the metadata, to make that, to represent it somehow.
All the pre and post condition stuff, right? If you define the pre and post conditions with an interface and not with a component, then if you have a new version of a component implement the same interface, the same pre and post conditions apply. So it cannot violate the semantics. Now, we all know that describing semantics with pre and post conditions is not necessarily trivial, and that you cannot describe all semantics, but that's typically also not needed in every project. But if there are certain aspects of the component semantics that are critical to be compatible in subsequent versions, well, then come up with metadata for it. It's not possible to define all kinds of semantics with metadata in general, but for certain kinds of semantics that is important for your system, you can come up with metadata or formal notations to describe them. It's not rocket science. I've done it, so it's possible. There's other stuff. For example, something that's kind of obvious is configuration parameters. If you look at executables in an operating system, then they have command line parameters. So the same with components. A component can have a bunch of configuration parameters which it reads at runtime to adapt its behavior dynamically somehow. And typically what happens is that the component defines the parameters, and the component instance, once it's instantiated or deployed, provides the values for those. Kind of obvious, but it's very important. Another one is ports. That's kind of not that trivial, but consider the following thing. Consider a component that, the kind of stupid example I always have is a component which transfers data from one database to another. So it needs to connect to two databases, and assume the database thing is also a component. Then it would have basically a required service, required interface. It would say, I need the database interface in order to do something. However, it doesn't need one of those. It needs two of them, because one is the source database and the other one is the target database. So it's often not enough to say that a component provides a certain service or uses a certain service. It needs to be able to distinguish different roles of using that service, kind of communication endpoints. And that's what you do with a port. A port is simply a named communication endpoint of a component which is associated with an interface. And then you can have several ports with the same interface, and they can be connected separately with other instances. Another thing that goes more into the interaction with a container or some hosting environment is some of the internal behavior. Is a component single-threaded or is it thread-safe? Does it have a life cycle? Does it need to be activated? Can it be shut down by the environment? Can it be passivated? What do you do if you restart? Can it be killed? Does it have state? Is it stateless, stateful? All these things might need to be specified, depending, of course, on your concrete component definition. That's the whole point of this discussion. You might have to specify these things so the environment can work with that sensibly. Another thing is how you want to wire the component instances. Are you able to say statically when you define the system that component instance A talks to some other component instance B, or should this be resolved at runtime? Like, I do have component instance A, and it needs to talk to somebody who provides this and that interface, and you can resolve that dynamically at runtime. That's what naming services and trader services in Corba and other environments do. So incorporating or distinguishing between static wiring and dynamic wiring is an important thing. The last thing I want to mention here in this discussion is, it's the last thing, but it's something called replicated state. When I was at a customer recently, they were building, they thought they were building a system that was basically based on message passing. So they had components and interfaces, and the interfaces were consisted of messages that went into components or out of components, the thing we discussed before. However, after discussing a while, we noticed, it's not really that they use message passing. What they really have is shared replicated state. Right? So there is some state in the system which is provided by a certain component, which is updated by a certain component, and then there are other components which read that state. So the intention of what you want to really do is you want to define that state, you want to define who updates it and how often it is updated, and you want to know who reads this state and how often it is read. So my customer people were so much in this message-oriented world that they were kind of trying to express replicated state with messages. And of course, you have to specify all kinds of things. You need messages that update a state incrementally or do a complete refresh and all that stuff. If they changed their perception from message-oriented to replicated state, then it's much easier. You just define the data structure and you say who publishes it and who needs it and how often you want to be updated. So we changed the meta model that described the component. We changed what we mean by a component to include a way of specifying that it creates and or uses certain shared state. And that made the specification of the system, it reduced the size of the specification significantly because you didn't have to deal with this low-level message exchange stuff. The abstraction was now shared state. So what I want to say is certain component architectures might also have the notion of shared state as part of their definition of what a component is.
Okay.
That was long.
So what other topic should we discuss? For example, the environment that you mentioned before. What kind of services does a typical component environment, also called application server very often,
or container.
what does it provide?
Again, of course, it depends on the domain in which you're working. Typical services is resource management, access to all kinds of resources like threads, network connections, files, whatever. And as it happens, there is a book that talks about resource management. I think you know it well.
Yes, I know it well, by coincidence.
So obviously, Michael is the co-author of this book. And it's about resource management and how to efficiently manage resources. And that's something the environment often does. Do you want to elaborate on that a little bit?
Yeah, it's about all the strategies that you need for efficient resource management. As Markus already started, a resource can be anything in that context. It's a thread, a piece of memory, or even processing time that you want to efficiently use and share potentially. And so there, in this book, there's a set of patterns that describe how to interact with resources if you have a certain focus on individual non-functional requirements. Like if you focus on real-time properties, you will choose a different set of patterns that avoid, for example, on-demand loading and load everything up front. Or if you focus on scalability, you will pay the penalty of not being so fast and so efficient, but you will be able to scale your system to a much higher number of users, servers, or whatever your scalability factor is.
Of course, we had an episode back in the day in the SE Radio podcast, and we'll link to it. So, well, yeah, so that's one big thing. In general, it's the job of the container to manage the resources, the life cycle of the component instances, and well, the access of the component instances to those resources. And again, as you said, these are different depending on the domain and what you really want to do. Examples include the stuff you already mentioned, things like virtualization. So making sure that the component looks as if it's still available, but in reality it's kind of paged out and reactivated on demand. Naming, identification is another thing that components get unique identifiers and you can address them if they have state. Remote access to components. This is the application server thing. There's, by the way, another book which we talked about in previous episode. Transaction management. Error handling, logging. So these are all the things that an application server or component container typically does. What you could say is that components handle the functional requirements, containers handle the non-functional requirements, and the metadata that describes the component makes sure that the container knows what to do with a component.
A topic that we didn't hit on so far, but is really exciting and sometimes causes long discussions in projects is the differentiation between a component and a service, like in service orientation today. Like some claimed, well, we don't do component-oriented software development or component-based software development. We do now service-oriented software development. Now it's your round, Markus.
First of all, in order to distinguish the two, we would have to be able to define both of them concisely, which we already noticed we kind of failed for components, and as everybody knows, is impossible for SOA. So that's the first problem. So I think there is one thing that is kind of important, and that is that in component-oriented development, you typically talk about, and that's not, it doesn't have to be like that, but that's traditionally how it's viewed. If you want to reuse something, what you do is you grab that component and integrate it into your system, basically by running it on your application server / container. In SOA, it's a bit different. What you do is you basically say there is these services running all over the world or all over the enterprise, and if you want to use it, you just remotely connect to it. But of course, I mean, I don't know, this is kind of not a hard distinction. Personally, I think SOA is primarily a bunch of hype, if you look at least at the technological stuff. In many ways, you can argue that service-oriented architecture is components done right, or it's basically the same thing, or it's a buzzword for it. I I have a really hard time distinguishing the two. One thing is that in SOA you have this explicit distinction between like services and then business processes that work on those services. But I mean, in a well-defined component-based system, you might have components which encapsulate process and other components that encapsulate more basic services, and then one calls the other. So in that sense, it's the same thing. I honestly have a very hard time distinguishing the two, and I personally think the component-oriented view with the metadata stuff we discussed above is more grounded in reality than some of the SOA hype. There's one thing I want to talk about briefly, and that is service-oriented architecture primarily looks at how a system provides a certain service. For example, if you look at the WSDL description of web services, which is obviously one way of building SOAs, albeit not the only one, then a WSDL 1.x specification only defines the services somebody provides. It doesn't define what somebody depends on, and that is because what you do define is actually a service, and a service is really just something somebody else can use. You don't define a component, which is something that provides the service and uses other services. So I think the best distinction I could come up with is that components can be seen as an implementation technology for SOA. A service is basically a bunch of things that others can use that you provide, and the component is actually the entity that uses a service or provides a service.
Something that pops into my mind is the SCA, the Service Component Architecture, which is basically what you just said, makes it more explicit and actually provides a programming model that exactly represents this view.
Right. So this leads us into the technologies, into the example technologies. SCA, the Service Component Architecture, is I think, a very, very good component architecture. It's, of course, labeled under SOA because that's today's hype du jour. But I think the idea there is, of course, that you define component types. You can instantiate them. You can connect them. Components can be structured hierarchically. They do use some other terms for some of those things. They have modules and stuff. But it's basically a hierarchically structured component model with then, of course, the ability to express or expose services in ways that are accessible to SOA systems like typically WSDL or some of these other things. So it's a rather new standard. I forget what the institution is that defines it. They have created a new institution for it. I forget what it's called. It's certainly something to look at. When I saw it first, I was actually really happy because I saw many of my own preachings in it. Because it was the first component, well, at least more or less recent component standard that looked at hierarchical deconstruction and some of these things, and distinguished between deployment and logical instantiation and composition versus types. So I think they've done a lot of things right.
Okay, so what other technologies? We had previous to this recording a discussion. And there I asked you what technology provides the bare minimum of a component model, and you answered Spring. So why is that? Right.
And it's not just Spring, it's basically all dependency injection containers. Because as we elaborated before, we said that the minimum that you need to do as a component is specify what you provide, which interfaces or services, and what you expect from your environment. And that is exactly what the Spring core does. It provides a dependency injection framework. The container basically doesn't do anything else. So it's kind of somewhat of a stretch to call Spring a container, but it does manage dependencies in both ways, and that's a good thing. It also does provide certain non-functional support for non-functional requirements, using Spring Core's aspect orientation mechanism. So you can basically deploy interceptors around component instances that then, for example, provide remote access to a component's interfaces or do some transaction stuff. So in that sense, I would say Spring Core with its dependency injection is the absolute minimum. Using its AO features, you can even add non-functional requirement support, or support for container handled non-functional stuff using Spring. So I would say that's kind of the minimum.
So if you rate Spring and Spring-like containers as the minimum, how would you rate EJB, COM, and Corba as some of the basically old guys today?
Well, let's look at each of them separately. EJB as we all know, is a direct competitor to Spring. The more current EJB release is 3. EJB 3 specifically is well, the Spring guys say it's not up to what Spring can do. Of course, EJB's guys say the opposite. But I think it's obvious that EJB, independent of the version, was one of the primary, first, and widely deployed component infrastructures, at least in the enterprise world, where you really had an explicit container and you had metadata description. They called it deployment descriptors, and you had your components were implementation of pure business logic. Yes, you had all those lifecycle interfaces and all that crap you had to write. It was early, people made mistakes, Spring improved on that. But I think that the general idea is there, and it did work well. COM is it's somewhat of a, well, COM isn't COM. There are many aspects. There is COM, there's DCOM, there's COM+, and basically it's a relatively early component model. It had binary compatibility or pluggability, and I don't know. It's very complex. The specifications with all those GUIDs and all that crap is not very nice. It's hard to use. It's tough to use. Don Box, kind of one of the gurus who used this stuff and who wrote about this stuff, once called it too complex. So it was an old model. It was basically the direct competitor to Corba, DCOM in case of remote communication. Corba isn't really a component model. Corba is first and foremost a remote communications infrastructure. And the Corba component model added a container to it where you could predefine certain lifecycle. The container came with certain predefined lifecycle schemes like, entity components which had state and stateless services which had no state. And then you could basically add metadata to your Corba objects, and then the container would handle them according to that metadata. So Corba components isn't used very widely. It's used in the defense world quite a bit, but not that much. EJB certainly is on its, well, I'm not sure, I wouldn't say it's on its way out, but it's not the only kid on the block anymore, because Spring really takes away quite a bit of its market share. So the technologies we talked about in the last couple of minutes are the traditional ones. Some are historic, some are traditional, some are still current. But it's important to point out that many of them still are somewhat minimal. For example, in most of them, there is no out-of-the-box way to describe certain different component types. Many don't support the notion of ports we mentioned before. The support for describing different metadata with regards to threading and active versus passive and stuff is very limited. Many can't have events. In some you cannot distinguish between static and dynamic wiring. Replicated state is something they all don't have. I'm a big fan of actually defining my own component model for a given project, because none of those existing standards, I think, does what I need. And more specifically, I cannot easily extend it. And that's more important. So let's briefly look at some maybe lesser known component-oriented technologies. One is the Windows Communication Foundations technology, formerly known as Indigo. It's basically a message-oriented system, but they also have components which define their interfaces as a set of messages they consume and provide, and then you can basically define message queues which handle certain different properties. You can have transactional queues, and I think they call these things endpoints. So that's actually a very interesting and really modern and actually nicely done component infrastructure, I think. Another one is Autosar, the automotive systems architecture standard. It's basically a component-based middleware for automotive embedded software. In case you don't know, a typical personal vehicle these days contains 50 to 100 computers, which are connected with various bus systems, CAN bus, MOST bus, and other bus systems. And of course, you need to have software in the car that works efficiently and that is distributed. And then you have all kinds of variants of cars and special equipment, and you have to not dynamically, but flexibly compose the overall system from components. And the Autosar thing is a standard there. Relatively new, I think 2003 was when it came out. And the interesting thing about it is that it's actually an embedded system. So the stuff we talked about is not limited to big iron enterprise stuff. You can use it in the embedded world. Of course, you have to implement things differently. You don't have this big application server. You maybe have a modular embedded operating system, which you then configure so it can handle the kinds of components you want to deploy on it. Another thing that I heard recently about is Android, the Google mobile operating system that's currently hyped quite a bit. And without going into too much detail, we'll put a link to a Google Developer podcast episode into the show notes. It's also component-oriented. They, again, invented certain terminology. They talk about intents and intent receivers and other stuff. I don't remember all of it. But it certainly is component-oriented and has many of the characteristics we talked about before. The last thing I want to mention is singularity. That's actually really cool. In case some of the discussions above sounded a little bit like, it sounds like components are programs and application servers and containers are basically operating systems. Yes, there is a relation there. So Microsoft has a research project called Singularity where they have built a completely new operating system using this metaphor of components and metadata and verifiable metadata and static security and code analysis and all that stuff. Extremely cool. And as it happens, the next episode of SE Radio will feature an interview with the primary researcher who leads the project at Microsoft, Galen Hunt. And we'll talk there about how Singularity kind of implements this notion of components. It's one of the reasons why we are having this component episode now in SE Radio. So because this is a good foundation for the Singularity episode next week.
Okay, anything that we missed?
Well, we have these esoteric questions, which we maybe, there is one thing that we didn't talk about yet, and that is, are component models a domain model for programming? And I think this is really a very nice analogy. If you look at today's hype around domain-driven development and domain-specific languages and some of that stuff, where people say you should understand your domain and then build languages around your domain so you can efficiently express algorithm structures and simply stuff in that domain, then if you consider software architecture the domain, which is what you should do if you're a software architect, then the stuff we talked about, the component stuff, is basically a way of defining a domain-specific language for describing your architecture. And by doing that, by defining the language, you understand, you formally define what a component is and what properties it has and how it works and how you specify it. And if you then use that language to define a specific system, you have, this is basically a sentence in the language. You define the architecture of a specific system as opposed to the language which specifies the abstractions you use for building systems. So kind of a buzzword that I like to establish here is like architecture as language, that instead of trying to write documents that describe an architecture, what you maybe should do is get together with your stakeholders and as you try to understand the architecture, literally define a language, define a grammar using a suitable tooling that allows you to describe instances of that architecture, certain systems based on that architecture. And by trying to define that language, what you do is you refine your understanding of the architecture and formalize what the architecture or what the capabilities of the building blocks, i.e. components, are. And I've used this in a number of projects, and it's amazing how well this works, because it allows you to express systems independent of technology, and it removes all kinds of misunderstandings. Because if people say, what is a component? You can point them to the grammar and say, a component is something, as you can see, that provides a bunch of interfaces, that requires another set of interfaces, that is single-threaded or multi-threaded. You can specify that. It can, produce events, and it has configuration parameters. So formalizing your architecture into a language is a very, very powerful concept, and components and their metadata descriptions are a really, really good starting point. And I hope that this episode gave you a bunch of ideas about what a component can have in its metadata and its functionality. We also have a bunch of slides that we'll put into the show notes.
Okay, I think this was a perfect end for this episode. Thank you, Markus.
Thank you.
Bye-bye.
Bye. Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the Podsafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.